So hello again. So this week's video is going to be just some stuff, some sort of observations about bugs, undefined behaviour and compiler errors. Just based on some stuff I've come across recently that I thought was quite nice ways to express how things work and what's going on. So for the first thought, just going to sort of offer a quick fact, which is if you have a program, a text file that represents a program, there are many, many more incorrect programs, syntactically and semantically, than there are correct ones. If you think of the absolute bare minimum of, say, a C program, you need the stuff, opening a main function, you can put some things in the body, you have to close the main function, you've restricted for a given number of characters, number of lines, you're quite restricted in what's a correct program. Just some random characters isn't going to be one. So, in some sense, there are many more incorrect programs you could write than correct ones. If you were just to hammer on the keyboard, chances are you get a program that isn't right, can't be compiled, isn't valid. Now, on some level, you can then think that a compiler is being asked to produce code from a text file which is in some senses a model for the code you want to produce. You can think of code as the thing, but in most senses the text in that file isn't actually a program. It's hopefully enough blueprint to produce a program. The compiler's task is then to take that blueprint and make an actual program. And you've got a bit of a question. If you give the compiler some invalid text, what do you want it to do? Would you prefer that it incorrectly think something's a real program and try and build it, or it incorrectly fail to build something that is a real program? It is unlikely you're going to produce a compiler that just perfectly identifies correct from incorrect and does the right thing in all cases. And in fact, while it might be plausible to check every correct program, it's not, but it can be done, they are countable. It's clearly not really possible to check every incorrect program because there's just so many of them. And in languages like C, C++, Fortran, all the classic compiled languages, the compiler writers, the language writers, don't consider it the compiler's job to identify incorrect code. They consider it the compiler's job to take correct code and build a program from it. And that's the way round they like to think and what they target. Now, this is really quite strongly parallel to the idea of errors in statistics, type 1 versus type 2 errors. So, if you've got a hypothesis, you want to do a statistical test to decide whether or not the hypothesis should be rejected or not rejected. No, we're not saying accepted, we're trying to be proper statisticians. A hypothesis survives for so long as you have not found grounds to reject it. And a type 1 error is when you incorrectly reject your null hypothesis. You have a false positive result. You have a positive result of no, reject that, but it is erroneous. Whereas a type 2 error is a failure to reject, again incorrectly. So you have a hypothesis that should be rejected and you didn't. So you can analogize this with all kinds of things. Maybe innocent until proven guilty is quite a good one. You would far rather that a court does not find someone guilty incorrectly, does not incorrectly charge someone, than you would that they find, and you accept that therefore there will be some guilty people who cannot be found guilty because you've decided that, preserving innocence is more important. And that's the sort of English law system. Various things don't work that way, but that idea is choosing one of these two and sticking quite hard to it. Now, in our analogy of a compiler, well, of course we have to choose a null hypothesis for this to mean anything whatsoever. And for a compiler, as most people would see it, as I see it, I would say you've given code to the compiler to compile because you think it's correct. You didn't just throw it in there for fun. You didn't just hammer on the keyboard and then hand it to the compiler and see what it does. You think it's correct. So the null hypothesis is this code is correct. So do you want your compiler to commit a type 1 error and reject your null hypothesis incorrectly, i.e. reject correct code and refuse to compile it? Or would you prefer it commit the other sort of error and compile code that isn't correct? And in a lot of things in computing, the decision is made to make sure you don't fail to act when you could. So it is that the compiler should compile code freely. It should always compile a piece of code that's correct. It should never reject correct code. And therefore, a consequence of that tends to be that, well, sometimes it will compile code that isn't correct. Some of that is because it's not possible to tell. It's not always possible to tell how a piece of code will react. Because, if you think about it, suppose you've got a complicated piece of code and there is one line in there which is just nonsense. You're doing something nonsensical. Well, if that line is never reached, never run in any invocation of the program, if it's wrapped inside a if false block, for instance, it'll never run. The program produced from that code is still correct. Do you really want a compiler to be trying to infer whether or not that line of code could run? And if it could run, it should reject the code as incorrect. But if it knows it can't run, then it could compile anyway, and it could rely on the fact that it's never going to run, therefore it doesn't affect the... You see where this is going. You don't want the compiler necessarily to be taking on all this load of deciding correctness. For one, it's a lot. Compiler writers don't want to do that because their focus is on compiling as much code as possible. And for two, you can get into a really, really sticky situation if a compiler refuses something that's correct. And nearly always that's, well, always by definition that's considered a bug. That would be a bug on behalf of the compiler because it has rejected a piece of correct code. You have to go back to the GCC lot or Intel and you have to say, look, your compiler's broken. And that's a thing that happens. I think, it's a sort of thing that happens to you maybe once every 10 years. You come across something that's reasonable, but a failure by the compiler. Far more commonly, though, what emerges is language standards evolve over time, new behaviour is added, and compilers might not yet get to the point of supporting that. So because most of the writers really want to compile as much code as possible, support as much as possible, they'll start to implement bits of a future standard, possibly before they're, fully able to implement them. So I've got an example that I'll show here, which is GCC, this is about 10 years ago, the version changed from 4.8 to 4.9. They were planning on putting in support for a C++ 11, I think, feature of regexes, regex checking in a library. GCC, I should be more precise here. Technically this was the library, the core library support. And they planned to release this feature in version 4.8, and they wrote in a lot of stuff to support it, but they hadn't actually finished it by the time it came to release time. And they had to make a decision: do we back out and try and remove it all, waste time, miss our release date, or do we just allow that we ship a broken feature? And for them, for various reasons, they decided that they'd ship a broken feature. And what happens is a regex is a way of checking whether an expression has a certain form, so you could use it to check an email address contains an at and contains a dot suffix and all of that sort of thing. And what you do is you form, the pattern of what you want, you pass it to a function that can then verify if a given string obeys that pattern. Unfortunately, in version 4.8 of GCC and its attached libraries, the question, does this return the pattern, returns false. In fact, the function to answer that question is just hard-coded as return false. And I came across this, and I was wondering what on earth I was doing wrong, and you look it up and you find, okay, it just does that. And, their argument is, oh, we documented it. They did. It's just one of those things. They failed, and they decided that the best way forward was to release. They decided that failing to act, failing to release, was a worse thing than releasing something broken. And this is them basically saying, we don't want to fail in the one way, so we'll just have to fail in the other way. And pushing ahead and, going on where perhaps they shouldn't. Basically, they considered it more acceptable to act wrongly than to not act. Similarly, they consider it more acceptable for the compiler to compile incorrect code than to refuse to compile, as I've said now a couple of times. So, what this kind of means for you as a programmer is it's up to you to produce correct code and give it to the compiler, and it's up to the compiler to produce a program from that. What, however, they do to help you out is the compiler can often spot things that are suspicious, that look, I'm using air quotes here, look dodgy, look weird, don't look right, are unexpected, and compiler warnings often encompass a lot of this stuff. And the reason they're warnings is that they tell you, but they don't stop, they don't error, they don't halt. It's up to you to decide if you want to fix the warning, if you consider it to actually be a problem or not. We do recommend very, very strongly use compiler warnings, turn them on, remedy them as much as you can. There are cases where a compiler warning is wrong, and that's why it's a warning, not an error. Because it can be wrong, what you're doing can be what you meant to do, but it just looks a lot like something that you probably didn't mean to do. And it gets a bit contentious because, people can't really agree on what things are suspicious, look wrong. Lots of them are things that you might actually be using as a hack or the old meaning of hack, a way of manipulating something to work better or differently. Anyway, compiler warnings, use them. If code is critical, do not accept warnings, because the problem with leaving warnings in place is they can hide more important warnings that you might have wanted. And if you find yourself doing some fiddling to just squelch a warning, fiddling with the code to just shut up a warning, well, maybe that's a sign the code's not good. Are you sure that it's safe to shut up a warning? Mightn't it change in future and not be? Similarly, if you leave a warning, are you certain that what it's indicating is going to remain not a problem? So you're saying now, yeah, I know it looks suspicious, but it's fine. Are you sure a future edit isn't going to elevate that from, yeah, it's fine, to actually, no, that's a problem now, and not be seen? So you really want to fix warnings. Anyway, this is the usual compiler languages. They decide that compiler should be like this. There are languages, Rust is one that is referred to most, I think, it's certainly the one I know the most about, where they take the opposite stance. They say, if a piece of text compiles into a program, that must be a correct program. And the reason they do this is to ensure that if you manage to get the Rust compiler to produce you an executable piece of code, it ought to be correct. Now, that means that you have to be really strict about what a correct program is. You have to actually reject lots of things that people might want to be correct because they can't be distinguished reliably from incorrect programs. It means that the act of writing the code gets a lot harder, but the debugging, presumably, hopefully, gets a lot easier because lots of classes of errors just can't sneak in there. On the other hand, it really does mean that getting your program to compile is a bit of a undertaking. And, you know, I think a lot of people, you write code, you try and compile it, you fix the errors, and when you finally do get it to compile, you certainly have a little moment of, you know, yay, I did it. With Rust, it's even more. There's a lot of that. Anyway, that is about making sure correct programs are correct. So this is compilers, but this does kind of propagate through a lot of computing. In a lot of things, it really is considered better to try and do something, to go ahead incorrectly, than it is to stop, to fail, to not act. So, for instance, a lot of people will code in a sort of semi-defensive manner by saying, okay, divide by 0 is a kind of error. I want to avoid this error. So anytime I divide by something, I should soften that division. I should add something or do something to it to make sure the bottom of the division can never be 0. And that's great if your problem is, you know, the number can get so small it kind of becomes 0, and you just want that case to be, all right, it's really small. But in a case where, say, you know, a number really shouldn't be anywhere near 0, adding that softening hides an error, because a divide by 0 error would have emerged, but now you've actually, you know, your number's much smaller than it should be, and something that could have told you about that has been suppressed. And the trouble here is, if you write things to silently tolerate issues, the issues will be silent. It's obviously, you know, tautological, but, you know, if you write things to be fault tolerant, they will tolerate faults. What you're aiming for is a nice happy medium of not falling over, but indicating that something is wrong as well. You know, things like exceptions and errors in code tend to get passed on through until something finally can't tolerate them, and that falls over. And if you let that happen, then you have to unpick some chain of implications to get back to where the problem actually started. And you make your life potentially quite a lot harder. Errors persist and spread and pop up in other places because you didn't catch them at their source. So defensive type programming, really being careful, often actually takes the Rust approach, where you have to fail hard and fail early. You have to refuse lots of things. You have to, sadly, produce lots of false positive errors in order that you don't let false negative errors slip through. So if your divide by thing is too small, you have to flag that as an error. And then you have to also handle the situation where it's just, you know, it's a small number. Separately, differently, maybe. Anyway, just some thoughts on some things, and I really do just quite like that tautology. You know, if you let errors be silent, then they're silent. That's a bad thing. You don't want silent errors. Scientific code is a lot less concerned about these things, but it still should be concerned about the idea of silent errors slipping into research, slipping out into data science, slipping out and not being seen, because coding has lent towards making them silent instead of making them not present. So hopefully some of that was interesting or helpful. Otherwise, we will be back when we're back. Thanks for listening.